So, good morning, everyone. So today's our session is going to be on regression mainly. You have done simple linear regression for your midterm, and today I'm going to be going over simple linear regression, and I'm going to be starting multiple linear regression and showing you a couple of commands that might be helpful for your homework this week. So, simple linear regression. So, what does it focus on? So simple linear regression, as you know, is for a single predictor variable. So you have to predict a value for a series of values for your predicted variable using one predictor variable. And so the equation for a simple linear regression would be of something of this sorts, right? So it will be y equals alpha plus beta times x plus an error term. So the alpha here refers to the intercept, and beta here is the slope of your x variable. So what does this slope indicate? Anyone? What does the slope signify? So the slope is significant of the number of units that y would go up or down by if you increase or decrease x by 1 unit, right? So for example, if my beta is 5, and that means that for every unit increase of x, y would increase by 5 units. So that's what the slope is significant of, be it simple linear regression or multiple linear regression, whatever that is. So that's what the slope indicates. And obviously, like any estimation, so linear regression is again a model, right? So as any other model, it carries an error term with it. And so I think we've worked on a simple linear regression model during the review session that we held for the midterm. And this is another one of the data sets that we found. So I'm going to be running this one. All right. So I'm view that data set for you right now. So this is the data set. So it has a number of houses, and you're going to be estimating the sales price of the house based on the appraised value of the house. All right. So here my y variable is going to be my sales price, and my x variable is going to be my appraised value. So like yeah.
Quick to point out, if you want to follow along with the data set, that's the same link that your other homework data sets.
Yes, yes. So
house values instead of.
yeah. So you just need to edit this one right over here from whatever directory that you've been using for your our scripts. You just edit the last one over here to house values.csv, and it should load. So that is our data set today. You can see that, I mean, just looking at the data, you can say that there is a positive correlation between your sales price and your appraised value. You can see that they're almost like very well linearly, related. So I'm going to be running a regression, a simple linear regression, to see how good this is. And the command that we've been using for simple linear regression in your classes till now is the lm command, right? So I'm just going to be modeling this using the lm command. Yeah. So how the lm command works is that you write your y first, and then you have the tilde, and then you regress it on your x value, right? So how do I know what the command has, I can type this, right? Question mark lm. That would give me what the attributes of that command is. So here that is. It goes to the R documentation. You can see over here that the formula, right? So the formula here, right here, is your y tilde x. And you can do this two ways, right? So what you can do is you can just write the formula and then you can add a data clause and instead of this way, right? So I can just do even this as an alternate, for example. Just sales price tilde. All right, and then I can put data equals houses. That can be done as well. This is an alternate and it's going to work the same way that this command does. So these are two ways of writing it, and yeah, I'm gonna just run this one right now. So yeah, so the simple model has been recorded in your R console, and now what you do is you're going to be getting the slope, the intercept, and the R squared values, and your p values for the model, right? So how do I do that? I just do the summary of the simple model that I just created. Great. Okay, so this summary right here would tell me a lot of things. So it tells me that the intercept of my model is 7.708 and that the appraised value's slope is 0.9482. So I'll just quickly write this on. So this model basically can be written as this, right? Sales price equals 7.708 plus 0.9482 times the price value, plus or minus whatever your standard error is, but you need not take that in the equation that you take. So that's going to be my that's going to be my equation. And you can see from here your p-values, right? So since this is a simple linear regression model and you have just one predictor variable, it's enough if you see that the p-value for your predictor variable is significant. How can you say that it's significant? It generally, yeah, so if the value is greater than your less than your 0.05, then it's significant. It'll basically show you these 1, 2, or 3 stars right next to it. So that's when you know that the variable is significant. And yeah, so that I've run, and I've also got the multiple R squared value, and the p-value for the entire model is exactly the p-value for the one predictor variable as well. So that will be my p-value. I can say that the model, the predictor variable is significant, and the multiple R squared is 0.7077, which is not a great value, but you can say that it's a pretty good fit. So this being done, what we'll do now is we'll look at the residuals, right? So we'll look at the residual plot of your x variable. So the plot will have your residuals versus the x variable, right? So that you use the plot command to get your residual plot, and the resid over here is one of the ways of writing to find your residual for your model, right? So I'll do that. So and I'll draw a line at 0, right? So I'll draw, it's an AB line command with horizontal 0. Okay, all right. So can you tell me how the residuals look like? Do they look random to you from the plot? Do you see any pattern in the residuals? Okay, so there is no apparent pattern in the residuals from that plot as far as I can see. And I can say that the residuals are randomly distributed. And I can also probably say that the residuals are more or less equally spread above and below your line zero. So that's always a good sign. That's how your residuals should be like. It means that your model is doing well. So next what we do is we plot the histogram of the residuals. So what do we generally plot histograms for? Yeah, so histograms are always a good check for the normality of your residuals, or even you can plot the histogram of your predictor variable as such to see if the predictor variable's data is actually equally distributed as a normally distributed. So that can also be done. So I'm plotting the histogram for the residuals right now. You can what can you observe from that? Can you say that it's normal? It's not, right? So you can, as you can see, so this is called the left skew. So there aren't many values over on the left hand side, and then it bulges towards the right and goes like that, right? So this is called a left skew, and yeah, so the data is skewed. So that means that your residuals are not normally distributed. So you have four specifications in your linear regression: the L, H, I, and N specifications. So these are assumptions that you make for linear regression. First, L is the linearity specification, and the second one is homoscedasticity, which is basically constant variance. And then the third one that you have is independence, and the fourth one is normality. So a linear regression should be in such a way that your residuals have an expected value equal to zero. That's your linearity specification. And the second one, homoscedasticity, is again the residuals generally need to have constant variance. That is, they should not have a particular pattern when you plot them against one of the predictor variables. The third one is the independence, which means that the residuals should be independent of each other. And the fourth one is the normality specification, which means that the residuals should follow a normal distribution, which you can clearly see from here. It's not normal. So I can say that this model violates the N specification. Do you have a question? Yeah, you can pretty much say all your four. I mean, you can pretty much guess all your four specifications with these two plots. The residual plot, you can also use the QQ plot, right? So that's also a test for normality. And histograms and QQ plots are generally used for normality. And then just by analyzing the pattern of your residuals, you can say about the other three specifications. Yeah. Independence?
Independence
Yeah.
is not a visual thing. It has to be taken from context. The data was collected in an independent manner.
Yeah. So independence probably requires a couple of other tests, but the other specifications can be found out by your plots. So so like I said, this histogram, right? So either you can specify it this way, resid of simple model, or you can specify it as simple model dollar residuals. It's going to work the same way. So yeah, so there's that, and then I plot the QQ plot, QQ norm. So how do you interpret the QQ plot? Anyone? How do you interpret the QQ plot for normality? It's a difficult question, isn't it? It just at least from this plot that I can see, you can't see much violation of normality over here. But like for this particular example, the better way to do would be to look at the histogram of the residuals rather than go for the QQ plot. But generally, in other models, you can observe some skewness over here. So it generally, um, can I can I call this? I don't know. It's just like from this plot, it's not. It wasn't like very clear to me whether they were normal or not. But I guess if you have other data, and you find that this is not like probably the range for this one right over here, it could be different. So it need not be like symmetric about your line over here. So that can probably tell you that it's not normal. But from this plot, it's not blatant. So I'll skip that. And okay, so this is what we covered for your mid sem, and after that, it's yes.
Can you just go through the all the types of
Homoskedasticity. Okay, perfect. Yeah, I can do that. So homoskedasticity can be found out by the residuals, right? So for example, so this is what they call it the tunneling effect. So um, I have my residual plot, right? That's my x variable, and these are my residuals. So that's my line at zero, positive values and negative values, right? I have points all over, right? Okay. So homoskedasticity is when your residuals, if you try to draw parallel lines to your zero, right? So it's when you don't have a pattern where your residuals are, say, this way. Can you see that this gives you a cone shape over here? It's expanding as you move out, or even if you have a pattern like this, right? Can you observe this? Going like this, right? So that means that they're not, the variance is not constant, that there is a tunneling effect that's observable. And generally, if your residuals fall, like, you know, the range of your residuals is constant up and down, then over values of x, then you can say that the variance is constant and that it is homoskedastic. Or if you observe residuals like this or like this, you can say that homoskedasticity is valid. So that's there. And independence, I don't think you can look through um, the plots and tell directly. And yeah, so linear specification can also be told by, for example, one of the ways of explaining your linear specification is from your summary or statement, how good your fit is by the R squared values, and also by the residual plot if you think that the residuals are randomly distributed above and below the line 0. So that should tell you the linear specification. All right, so we'll move to multiple linear regression. So what do you think about multiple linear regression? Do you view it as an extension of a simple linear regression, or do you think it's a little different from the simple linear regression? Yeah. So the interpretation of slope in your multiple linear regression is a little bit different from your simple linear regression. All right. So what we have here is a lot of variables, a lot of x variables, right? So you are practically like all the regression problems that you're going to be solving in life, they generally won't be a simple linear regression. So if I take the sales price of a house, right? So the appraised value of the house is not generally going to be the one predictor that determines the sale price of the house. It's going to be like how old the house is, if you have parking space in the complex or whatnot, right? You have a lot of predictor variables that decide the sales price of the house. So Yeah, so a multiple linear regression model can be expressed like this. It's, yeah.
Could I just point one thing out? So notice the outlier in the bottom, and then we saw him in the histogram as well,
Yeah.
right? Why is that a problem? Is that a problem? I guess my question is yes. That's going to skew the model, right? Yeah, that's this same point. And the problem is a large outlier like that is going to distort the rest of your model as well.
So when you find outliers like that, you can always, like, if it's one or two of those outliers, you can remove them from your model. That's not the best solution.
But you need to state explicitly in your write-up of your report on the model that you remove this point and why.
Yeah.
Because if you remove that point, you meet the rest of the checks, right?
You're probably going to get a better fit to the model if you remove that. That'd be.
And I mean, if you were the original data collector, you could go and investigate what was wrong with that point, right?
You, the general way is not to remove the outlier, but try to fix it. But it's generally not preferred to remove your outliers. But yeah, for the sake of your homeworks, you can always say that as a way of correction, it's to remove an outlier.
The correction would be pretty explicit if it was going to be done like that.
Yes. Oh no, that's normality, right? So that outlier is what's like outliers like that are what's gonna give me the skew over here. So yeah, that's gonna affect your normality specification mainly. Okay, so multiple linear regression. So it's an extension of your simple linear regression, but the interpretation of your slopes is a little different. Uh, it's y equals alpha plus beta 1 x1 plus beta 2 x2 till how many ever predictors that you have plus an error term, right? So how do I interpret the coefficients in a multiple linear regression? How do I interpret this beta 1? How do I interpret this beta 2? Anyone? So the intercept, I think it's pretty obvious. It's just the value that y is going to assume when all your predictor variables are zero, right? So that's going to be my intercept. If all my predictor variables are zero, then all these go to zero, and whatever alpha is left of there would actually be my predicted value. But how do I interpret the slopes? Okay, so the slope, it's a little bit different from your simple linear regression model. So if I consider beta 1, right? So beta 1 is the amount that y would increase by if x1 is increased or decreased by 1 unit, right? Keeping all other variables as zero. So it assumes that this is something like a marginal increase or a decrease of y for that particular x variable, keeping all of the variables as zero. So for example, if beta 1 is again 5 over here, then my y is going to increase or decrease by 5 units if my x1 increases or decreases by 1 unit, keeping all other x's as zero. All right. So that's the interpretation of the slope in your multiple linear regression model. So, all right, okay. Or a zero, or even rather, like they remain the same, right? Or like they need not be zero, right? So the other x variables should remain the same. Is the point? They shouldn't change in value as well. Then it won't be. Then your y won't increase by just beta 1. That's what it means. So so this data set again is an extension of your simple linear regression data set that I just did. So it introduces two more variables apart from your appraisal value of the house. It includes square footage and the number of bedrooms of the house that determine the sales price of the house, right? So this is again going to be the same. It's from the same GitHub repository. You just need to change this to housesextended.csv, and that should open it for you. Okay, so I'll run that one right now. I'll view the data set. So, okay, so what you can see here are three predictor variables now. The price being your predicted variable, your y variable, and your x variables being appraised value, square footage, and number of bedrooms. All right. So we did talk about the fact that the price and the appraised value seem like they were positively correlated, but we don't know how adding your square footage and the number of bedrooms to the model would affect the relation between appraised value and price either. So we'll figure that out now. So, okay, so I'm naming it as full multiple model. So I'm again using the lm command. That's what you use for your multiple linear regression as well. So I'll model it as price to appraised value. So when you have more than one variable, predictor variable, or you just add a plus in between the variables. So if you add a plus in between your variables, that's going to give me a multiple linear regression. So what I did here was price to appraised value plus square footage plus number of bedrooms. Data equals house extended. That's what. Yeah. Um, okay. Data equal to house extended, right? So I'm going to run that one now. All right, it's run. And the summary, I'll view the summary now. How do I do that over here? Can you help me? All right, okay. Okay. Can anyone see that? All right, okay. So how do I interpret this summary over here? So you can see over here that you have an intercept on and all your other three predictor variables as well, right? So it's just not one predictor variable now. You have three predictor variables, and hence three p-values for each of your. For one p-value for each of your predictor. What you can see from here is that the number of bedrooms is not significant. It's the p-value for the number of bedrooms is 0.277. And you can also observe that the multiple R squared value is 0.7714 as opposed to 0.70 of your simple linear regression model, which means that this model is better than your simple linear regression model in explaining the sales price, right? So, yes. Mm-hmm. Yeah. So if the p-value is greater than 0.05, it means that that predictor is not significant in predicting your y variable. So, what can be the remedy now? Now that I know that number of bedrooms is not significant, it's not a significant predictor, can I remove that from the model? I can remove that from the model, right? So, observe right now that the multiple R squared value for this model is 0.7714. And I'm using three predictors, and you found that the number of bedrooms is 0.277. The p-value for the number of bedrooms is 0.277, and hence you want to eliminate that. So I'll do that now. So this will be my reduced model. So reduced multiple model is an lm command again, price of appraised value plus square footage. I'm removing the number of bedrooms from the model. and data equals to house is extended, right? So I'll run that and I'll get the summary. Okay, so what does this tell me? Now I get to see that both the predictors that I've used are significant, right, in explaining the sales price. And you can also see, as a comparison of this one and this one, you can see the difference in your intercept, right? The intercept has gone up, and your appraised value has probably gone down a little, the slope for your appraised value, and the square footage's slope has also gone down. So and you can see that the multiple r squared value actually for this radius model is a little less than the multiple r squared for your full model. Does that bother you? Now, do you reconsider removing that third variable that was not significant from your model? The r squared value has, I mean, it has reduced. Does that bother you? Sorry? Yeah. It's not by a lot, exactly. So if, for example, if it had reduced to 0.60, it's not possible for it to reduce it to get reduced to 0.60 because that variable was insignificant in the first place. So if don't worry if your multiple r squared value has come down by a little. This is still a better model than that because think about it. Like in a real life situation, when you have to model with say 100 predictor variables, right? You'd want your model to be as simple as possible, and you can compromise on the r squared value. It's just a small decrease from 0.77 to 0.769, right? So it's a very small decrease, and you can always compromise on the r squared value if that leads to a simpler model. So that's always something that you need to keep in mind. Yes. So okay. So how do you interpret the intercept for the radius model? Anyone? How do you interpret this number 5.538? That would be my sales price. So it's actually the sales price is in thousands of dollars, I guess. Not really sure. I'm not sure what the unit is, but yeah. So that's basically my that's the interpretation of my intercept, right? So yes. Now we'll talk about confidence intervals, right? So I want to find the confidence intervals of the predictor variables at 95%. And for that, I use the confident statement, right? So the confident statement would basically, yeah, so I'll show you what the confident statement. So, okay, so the usage of the confident statement goes like this, right? So you have the object, which here would be my reduced multiple model. And then you'll have a specification for which parameters are to be given confidence intervals. You don't have that right now because you're giving it for all your predictor variables at 95%. So if you include this PARM statement and you type one of your predictor variables, then it's going to give the confidence interval for that predictor variable. But if it's missing, all the parameters are considered. That means all the predictor variables are considered. So level is the confidence level that's required. So that generally is 95% that we take in all our exercises. But if you're asked for a different level, then make sure you specify a different number over here. With 90%, just specify 0.90. All right. So I'll run the confidence statement now. Perfect. Okay. So this gives me the appraised value and the square footage values, right? So, or rather, this gives me. I'm sorry. Give me just a second. Yeah. Okay. So this gives me a confidence interval of the slope, right, for my predictor variable. So at 95% confidence interval, I can say that the appraised value slope lies between 0.556 and 0.800. And similarly, at 95% confidence, I can say that uh, my square footage is slope is between 1.47 to 2.83. So you're gonna be getting questions like this on your homework if you've already started it. You know. So that's going to be one. Okay, so now what we'll do is we'll go for estimation, right? So given values for my predictor variables, I want a value for my sales price. So if I'm assuming that a new customer, a new house has come into the market, right? So I'm assuming that the square footage of the house is known, the appraised value of the house is known, and the number of bedrooms of the house is known, or whatever that is, right? So now I want to find what the sales price of that house is. So it's basically like addition to your existing data set, right? So for that, I use the predict LM statement. So I want to estimate the sales price for the house at 123 Lotus Avenue, which is appraised at $150,000 and is 2,500 square feet. And I want to give a 90% prediction interval. So there's a difference between your confidence intervals and your prediction intervals. I'll tell you what that is. I have that down. I'll tell you what that is. But uh, I want a 90% prediction interval and I want to estimate the sales price for that house that's given your appraised value and your square footage, right? So I use a predict LM command. So I'll tell you what this command consists of. Okay, so the predict LM statement consists of these classes. So you have the object, right? You have to define new data. So new data is basically a vector that you're going to be defining, a list that you're going to be defining, where you add values to your predictor variables and then add this new data list to your predict statement. All right. So you have the object, which would be again would be your appraised. Okay, so yeah, so your reduced multiple model would be your object, and then your new data. I'm defining new data over here as a data frame, and yeah, you have a lot of these, right? So you have interval. Okay, so this interval basically is what is used. So if you specify prediction within this interval statement, that's going to give me a prediction interval. And if you specify confidence inside, that's going to give me a confidence interval. And the level is at 90% because that's what it's asked for. You're asked for a 90% prediction interval. So I run that. And okay, so what I need to do first is I need to define a data frame or a list that would help me with this predict LM statement afterwards. Or if you can do that even inside the predict LM statement, but I'm just doing this outside the predict LM statement. So I'm defining new data as a data frame with appraised value equals 150 and square footage equals 25. All right, because I think your all your data has been given in, for example, this square footage is in hundreds and your appraised value is again in thousands of dollars. So um, yeah, so I'll give this, I'll run that command. Okay, so it's now stored a data frame having appraised value of 150 and a square footage of 2500. So I'm going to use the predict LM statement now. Yes. Okay, so I'll use a predict LM statement now. I'll run that. So what do you get here? So it gives you three values over here. It gives you a fit value, it gives you a lower bound and an upper bound. So the fit value is basically the exact prediction value without the confidence of the prediction interval, right? So if I use that formula, right? So Okay, so if I use the formula, sales price equals 5.538 plus 0.678 times $150,000 plus 2.153 times 25, is it? Yeah, 25. So that's going to give me a value of 161.1674. And your lower and your upper bound on that is basically your prediction interval that you giving a leeway, sort of like a slack to estimating your sales price, right? So, what is the difference between this prediction interval and this confidence interval? So, a prediction interval basically tells you about the distribution of values in a particular prediction, right? So, what have I done here? I've taken the value I've taken an appraised value and I've taken a square footage value, and for that particular prediction, I'm getting an interval. So that's the prediction interval. It does not take into account the mean. It does not take into account the uncertainty in determining the population mean. But then a confidence interval tells you about the uncertainty in determining the actual population mean. So if I, for example, changed this statement from prediction to confidence, right? I'll run this. So okay, the fit value is going to be the same because the fit value, like I said, it's obtained from the model's formula or whatever that is, right? But then, can you observe that your confidence interval is actually narrower than your prediction interval over here? Your prediction interval is 148.9 to 173.35, and your confidence interval is 157.79 to 164.54. It's tighter, even though you've specified the same level. You've specified 0.90, right? So generally, your prediction intervals are wider than your confidence intervals for the same level of confidence. So yes, so all these are going to be helping a lot with your homework this week. I'm assuming that the data set is going to differ, but then a lot of commands that we used in the session today are what you're going to be following for your homework. So I hope that would be useful for you guys. Any questions? I'll be sharing this our session with you. Any questions? Yeah. Proportion of variance explained. It's asking you basically how good the fit of the model is and what's a good estimate of the fit of the model. The proportion of variance in y as explained by your x variables. What is a good measure of the proportion of variance, or rather, what is a good estimate of? I mean, which of your values from your summary statement explains how good your model is fitting? So the R squared is basically a measure that would explain the proportion of variance. Any other questions? Yeah. 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 So actually, what you can do is you need not do this over here. All right. So I'll give you another way of doing this. What you can do is new data equals, right? Because like yeah, exactly. So what you can do is this is an alternate. You can open a list, all right? So and you can say appraised value equals 150, comma, square footage equals 25. Intervals confidence and levels 90. And if you're going to run this, it's going to give you the same answer. So you need not define a data frame outside of the predict.lm statement. You can do that even inside, but make sure you use the list function. I'm not sure. Probably data frame works as well. You might want to try that. So yeah, that's another way of writing the predict.lm statement. Any other questions? Yeah. So what was my actual value in the row 10 of the data set? You observe the y from the row 10 of the data set, right? Yeah, okay. And you need to use this model and the predict statement to obtain the fit value, right? That would be the predictor value. And the actual minus the predicted value will give you the residue. Sorry. Remember that it's the actual minus the predicted value and not the other way around. So if it's negative, then it stays negative. Any other questions? Alright, so that will be it for the tutorial today. I hope you guys found it useful. I mean, I'm pretty sure you'll find this useful when you're solving your homework, because this uses a lot of the same commands that are on your homework. There's going to be a difference in data set and some other parameters. So yeah, so that's about that. Thank you.
You have to pan over the next page.
Over here.